On this problem, one of the things you needed to do is find the distance the ball would need to travel to the corner pocket. You have the dimensions of the billiards table, and you can find the diagonal length. There are two ways some of you looked at this problem. The first is that the ball exhibited slipping all the way to the corner pocket. The second way is that the ball underwent slipping for some distance and then transitioned to forward motion without slipping. So what are the forces, accelerations, or velocities in this problem? We have v sub g, which is the forward velocity of the ball. This will be broken down into two components, being the initial v sub gi, where the ball is undergoing slipping, and the final velocity, where the ball is not undergoing slipping. We will also have an initial and final angular velocity of omega initial and omega final. We need to look at the time it takes the ball to stop slipping from the initial impact and the time it takes the ball to continue rolling till it finally stops. We also know the total distance the ball has to travel, so you need to find the total distance the ball goes until it stops slipping and the n velocity v sub g when it starts the non-slip motion. At this point, your ball is moving in a linear fashion where you can use standard motion equations with a new vg and a final v sub g equals 0, so the final velocity when it ends and stops, using the remaining distance to determine if your initial vgi is good. Let's account for our variables now. So the first variable is v sub g1, which is the initial velocity where the ball is slipping until it stops slipping. V sub 2 is the initial velocity of the ball after it stops slipping and undergoes normal roll. V sub 3 is where the ball is equal to 0. The first acceleration is the initial deceleration during slipping. The second acceleration is deceleration during non-slip to end of travel of the pocket. T1 is delta t during slipping, and T2 is delta t during non-slipping. So working our way backwards, we can look at the distance for the non-slip distance to the end of the table. Also the first part during the slipping will look the same, the d-slip distance. Also look for v sub g2 from v sub g1. We use the velocity equation since this section deals with angular velocity and acceleration. We need to incorporate that into our solution so we can look at the moments of the ball from moments of inertia. And we also know that the force in the x direction is opposed to by the frictional force due to kinetic friction. We have the following equations, and then we get the two following equations for acceleration and angular acceleration. Another part of our solution is to look at how the ball responds during pure rolling. We have the following equations for velocity equal to the angular velocity times rotation. We have the formula for inertia for the cue ball, and we can use the formula now for angular velocity. W2 is equal to angular velocity 1 plus the angular acceleration times time. You rearrange the equation for t, and you can find the time it takes to stop rolling during slip motion. So your final numerical solution will have two parts. Your total distance, which you have measured from the billiards table, will be equal to the distance that's traveled during the backspin of the cue ball plus the distance of rolling forward. So you have everything you need to solve this problem, which is the looking for the total distance being equal to the distance of the backspin plus the distance of the pure roll and forward motion. And I hope you found this solution entertaining.